1 standard deviation.
I plus or minus 1 sigma. And so what you do is you interpret sigma is the standard deviation. Right? And sigma squared is called the variance. And Eric, this is where you were going. All right? That sigma squared equals the summation over I of, if it's x, it's going to be, xi minus x bar squared, all divided by n minus 1. So if you take the square root of that, that's what you were talking about for the standard deviation.
Yeah.
Right? All right, but what happens is Griffith shows, and I want you to follow, this is also what I need you to do, is I need you to follow these arguments of Griffiths. I know, David, you were working on this before. All right, that you can show that sigma, so over here, I'll do it over here, is that sigma, for this distribution, sigma, the standard deviation, equals the square root of the expectation of I squared minus the expectation of I quantity squared. Okay, so you should go through equations 10 through 1 through 12 in Griffiths, and you should be very comfortable with them. Okay, let me take a step back and say some words because everybody looks a little confused. All right? If I have a distribution of data like this, can I calculate an average?
Yes.
Sure. Can I calculate a standard deviation?
Yes.
Okay. Here's how you calculate the average. Right? Here's how you calculate the standard deviation. Right? So this, you could calculate the standard deviation of this data this way. Right?
Which is a pain.
It's a pain in the butt. So what Griffith shows you is that this is the same thing. In fact, to get this, you have to start out here. Okay, so am I doing anything more than standard statistics? I'm calculating an average and a standard deviation. Doing nothing more.
I have one of the questions we probably give us for homework assignment was using this assignment, this one.
Yeah, this
calculate
is a big old deal on this.
everything.
Yeah. Yeah. Definitely. I mean, I want
And it is
to.
enlightening.
First problem you gave us had to do with dealing with this,
Yes, yeah.
calculating this stuff.
Yep. So now, I mean, I want you to have it for it. I don't want you just all to be able to calculate. I want you to have a feel, so you should know what it is. All right? And this group is that we're going to be dealing with functions that are probability distributions. So we're going to want to know what the average is, which is called the expectation value. But then the other thing we want to know, what does the standard deviation give you an idea of?
The spread.
Kind of the spread. Yeah. So, but we're going to use it as an error. The spread is also an idea of the error. Right? Remember, the standard deviation is a measure of actually precision. We've done this before.
So it's a measure of the width of where the wave function collapses.
It's a precision of your measurements. You're going to calculate essentially an average, right? And then we know that the average is just an average, but we want an idea of that precision, or the,
So I feel like I'm running some of this for experimental.
Yeah, it's all experimental stuff. I do it in way more detail for experimental. All right, so this is the key things that we need to know for discrete probabilities. All right, now we're going to move over to continuous probabilities. And the continuous probabilities is a very nice step, and essentially gives us quantum mechanics. What we do in quantum mechanics. All right, we're left already with the question of what does it tell us. All right, now we're moving on and doing something with it. Okay, so here we go. And again, following Griffiths, what if instead I said, what are the number of people with birthday on such a day. Alright? So the first thing I can do is go 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 365. Right? And I'm going to come up with bins. I don't know what the bins look like.
Either weeks or months or whatever.
Okay, so that is argument. And very definitely we've come up with a discrete probabilities like this. Alright, but what if he went further? What if he said not just day, but what if we also say not just day, but hour? Alright, so now we've got to take this one bin over one day and divide it into 24 small divisions. Right? And then if I'm like, wait a minute, not just hour, but minute. Right? Then I have to divide it into 3,600. And then if I went even smaller, all the way down to nanosecond, I get even smaller. Right? So my bin is getting smaller and smaller and smaller and smaller and smaller. Right? What's happening to the probability of getting a hit
It's getting smaller.
in now in a given bin?
Smaller and smaller.
It's getting smaller. So in other words, the probability sub I is proportional to the bin size. Right?
Right.
So I'll call it d bin, or here d time. What did I say in my notes to me? I said dx. I don't know why I said it in my notes. It's probability dx, where the bin size, the width here, is not seconds, it's x. Right? So the probability is going to go with this.
You could just as well make it time, not dt.
Right, so good. If you start thinking like that, then you're free, because you realize that the math is very general to a lot of different physical situations. All right, so if I have probability over here, right, and over here I have units of length, my probability is proportional to the units of length, how much length I'm taking. What do I need in front of this?
Integral time?
I don't need an integral yet. Well, so let's do that.
So
And let's go further. Let's call this dp of x. I like that better. It's the tiny bit, it's the tiny chunk of probability at some place x. So here we are. Here's a little dx. All right? And so what I'm looking for is how much probability is in this little chunk. What is the probability at this x?
Right, well you have probability on that side, then you have x on this side, so you need probability per unit
I need
x.
a probability per unit length over here, right? So in other words, dpx has to equal some density, all right, a probability density, where the units of the probability density have to be probability per unit length. So dpx was the probability per unit length, probability per unit length times the length. Cross out the length, and that gives you probability equals probability.
Right.
All right. Now, in that limit where we take all these bins and we make them little discrete things, you can imagine that in the end, instead of it being chunky, it is going to be continuous.
Probably more wavy than that.
Okay, probably more wavy. Yes, I'm just doing that.
Yeah, it's not supposed to be a bell curve, is it?
What's that?
Yeah, that looks cool.
It could be a bell curve. Why
Well,
not?
not for ages.
Yeah, not for ages for sure. All right. So yeah, I agree. Unless we had very, I mean, it could happen.
Yeah, it's
not
entirely
very
possible.
likely. Yeah, it's not very likely.
That's the baby boomers right there in the middle.
Yeah. All right. And so what we're going to say then is that density, what we know from the experiments that we did, what we did with the double slit. So when we did light with a double slit, we came down to d probability equals e squared dx. And we also came down for particles. A little tiny chunk of probability came down to psi star dx. Right? Alright, so we can see what we're doing here in quantum mechanics. This thing has to become, what is that?
That's your wave function.
Okay, it's the probability per unit length. And is it the wave function?
It's wave function squared.
It's the wave function squared. Right? Because, so check this out. This has to be your wave function squared. Now, let's do this. So if I square my wave functions and I get probability per unit length, right? I can back up and I can say, what is my wave function? First of all, what are the units of my wave function then? So if the wave function squared is probability per unit length, what are the units of the wave function itself?
Square root of probability per unit length.
Right, so what the hell is the square root of probability? I don't know.
I have no idea.
I don't either.
Okay.
But that's what we solve for.
Right.
Okay.
Right? So that's what we're solving for. That's the wave function. So that leads to another question. That gives us more of a reason to say, my intuition is no good on what the wave function really is. Right? I don't know what it is. All I know about a wave function is that when I square it,
It's all you know is
Yeah,
the
okay.
wave function is the square root of the probability.
right,
Whatever
but
that
what's
is.
interesting with light, I have no problem calling that thing that I don't know the square root of the probability, the electric field.
Ah.
Right?
So maybe we should set up that league.
So it's sort of a
Yeah.
particle
Alright.
field.
So, yeah, we can do whatever we
It's
want.
the electron field.
Yeah.
Alright, so this is going to be psi squared. Okay? Now, following the analogy over here, if I go from a summation of discrete bin sizes, I'm now going over here to a summation over infinitesimal bin sizes. So how am I going to be able to calculate the expectation of I, for example, for discrete distributions?
You can integral on this one.
Okay, so I'm going to go from the summation over I of pi times I, and I have to go to the summation, which is going to be the integral of, if you want, dp I times I. But what is dp, the little tiny chunk of probability? It's psi star psi dx, which equals the integral of psi star psi dx. This is the little tiny chunk of probability times I or f of I, times I or f of I. Okay, so in quantum mechanics, to calculate the average of some function of I is going to equal, here's what we've got so far. Let's say we're going to find the average between A and B, points A and B, of f of I times psi star psi dx. Right? And then how am I going to once I calculate the average? Well, now let me kind of let me give you a caveat here. Okay, the goal is to calculate your variable I and multiply it times dp. Alright, but in quantum mechanics, what we're doing is everything with operators.
Yeah, you make an average f of I.
Yeah.
Alright, that's the average value of the function you're saying?
Of some function, yeah.
Alright, got it.
Alright, but when over here I have the probability, but I have this functional form. I don't have the explicit value of it. Alright, so here's what I'm going to suggest. What I'm going to suggest is the proper way to do this calculation. A to B of psi star, and then f of I operator times psi times dx. So what I'm going to do is I'm going to sandwich it between those two. Right, and I'm going to turn it into an operator. Psi, and it's an eigenvalue